3D finite element analysis of pile behavior inside the deep excavation in soft soil. Abstract: a large excavation was carried out in the thick soft soil layer to construct the pile cap foundation and the basement floor for the 15 stories building in Ho Chi Minh City. The soil profile consists of a 25-meter thick of very soft clay with SPT value of 0 laid on an 8.5-meter thick of soft clay with SPT value of 3 and laid on a 13.9-meter thick of medium-dense fine sand with SPT value of 17. The excavation was supported by the system of 6-meter depth SP, 4 steel sheet piles with the tied-back rods on the top of the wall to the 6 mH steel piles installed behind the wall. Before the excavation, the spun PHC pile with 600 mm diameter and 100 mm thick was installed to support the superstructure. As excavation to 3.8 meter depth, 4 piles with the distance 4.55 m, 7.15 m, 10.65 m and 13.25 m from the wall had the top pile displacement 63.5 cm, 38.86 cm, 19.5 cm, and 11.4 cm, respectively. Furthermore, all these piles were determined to be cracked by using the pit test. Based on the collected data, back analysis was carried out by using PLAXIS 3D foundation with Hardening-Soil model to determine the response of these piles during excavation. In the results, the maximum bending moment of these piles was over its ultimate value. Thereby, we can analyze the reason piles group in this building was failure and use the parameters in PLAXIS for expanding the analysis to other situations. Keywords: failure, steel sheet piles, excavation, soft clay, bending moment. Introduction. In Ho Chi Minh City, a large number of high buildings with the basement floors were constructed to supply the living houses and working offices. Ho Chi Minh City lies on a complex stratum with the soft clay layer somewhere is thicker than 30 meters. Therefore, a lot of problems were happened during the excavation process to build the basement floors for the high building. Some works have taken place the failure of inside existing piles due to the deep excavation. In 2007, all the installed piles to support the superstructure of Thao Dien building in District 2 Ho Chi Minh City were tilted during the basement excavation. A 13 stories building in District 7 has the PHC pile top move 0.6 meter when basement construction was carried out 9. Similarly, the silo cement in Heap Phuc Industry Zone used the spun PHC pile with pile length from 33 to 35 meter through the thick soft soil layer had about 80% of piles under the silo were tilted in the same direction. A number of 2,664 piles among of 7,474 piles of the water treatment station in Ben Chan district had the top horizontal displacement in the excavation process 9. In 2011, a 15-story building in District 8 built on the ground with 2.5 m deep of soft clay, the piles near the steel sheet pile wall was tilt and beak out during the pit foundation excavation. The maximum top pile horizontal displacement was up to 0.6 meter. Analyzing the failure of pile inside deep foundation pit in soft soil is a considered problem. The deep excavation in soft soil is very complicated. The lateral displacement of soft soil produces the passive pressure on pile. It causes the pile movement and bending moment greater than capacity moment of the pile, therefore, the piles are damaged. According to Koch St. 2009, there are 3 common methods for researching about the effect of excavation to the nearby pile foundation: the finite element, the centrifuge test and the field test 1,4. Poulos and Chen, 1996, did analysis by using of the finite element method analyze the response of piles due to unsupported excavation-induced lateral soil movement in clay 2. This method was also used in back analyzing to the responses of piles subjected to horizontal soil movements in clay, and many researchers use finite element method for their own studies. Finite element method is easy to progress, and the result less fluctuate and appropriate with reality. However, the result from this analysis is affected by many factors that are required experience and understanding of not only geotechnical issue but also solutions and software. Recent efforts in centrifuge modeling of passive piles adjacent to unbraced excavation was done by Leung, Ong. Initially, Leung, 2000, presented the results of centrifuge tests of an adjacent single pile behind an unstrutted stable and failed wall of a deep excavation in dense sand. The research also investigates the influence of head piles fixity for behind the stable wall. The pile head deflection and maximum bending moment for the free-headed pile decreases exponentially with increasing distance from the excavation. Subsequently, Leung, 2003, extended the centrifuge test to pile groups, incorporating the effects of interaction factors between the piles with different head fixities. Following Leung, 2000, further investigation was done for single pile behind stable wall, Ong, 2006, and instable wall, Leung, 2006, in clay 5,6,7. Fino et al., 1991, and Go et al., 2003, executed the field test. According to Go, 2003, used movement measurer for soil horizontal displacement in actual field and examine the behavior of an existing pile due to nearby excavation of a 16 m deep excavation. The results of movement and bending moment of piles between observation and predicted by pile program was quite similar. 3. Considering the influence of deep excavation to piles inside the foundation pit, Thasnanipan, 1998, presented 4 case histories of pile damage associated with excavation works in Bangkok soft clay 8. The failures were examined by high-strain dynamic load test and also modeled by a two-dimensional finite element to predict the response of the piles. Since then, finding a correlation between the location of cracks and bending moment in the pile exceeds the allowed bending moment. Besides, Kok, 2009, presents a case study in West Malaysia for passive piles failure in very soft marine clay in open excavation due to soil displacement. Kok, 2009, used PLAXIS 3D foundation software for back analysis. Hardening-Soil model was used in analysis. The analytical result of excavation phases was compared with the cracking moment resistance of piles. Kok showed that 70% of modeled piles which have axial bending moment caused by pit construction exceed the pile's cracking moment, and the result was all the pile are cracked. The cracking position occurred in adjacent layers between weak clay and hard clay. Nowadays, a lot of deep excavation have trouble in the construction process due to the large displacement of soft soil causing excess load on the pile bearing capacity and make the failure of piles. Therefore, analyzing the failure reasons as well as finding suitable alternatives for construction excavation without affecting piles in deep pits is an issue needed to study. Owing to that reason, this paper analyzed the horizontal movement of piles, the largest bending moment in pile of deep excavation construction in soft soil in Ho Chi Minh City, District 8 by finite element method with Hardening-Soil model. The analysis result will be compared with the observation data to show the soil model and data appropriate for design and apply for analyze for the same constructions. To analyze the failure of piles inside excavation. A project description. The residence building in District 8, Ho Chi Minh City have 15 upper ground floors and 1 basement floor sing the pre-stressed reinforced concrete spun pile foundation to resist superstructure. The foundation pit is 52.4 m long and 33.9 m wide and 3.8 m deep, was constructed by braced excavation method. The 6-meter long SP, 4 steel sheet piles was installed to retain the excavation during the basement construction. The main construction includes 4 main steps as shown on the figs. 1 to 5. B. Geological characteristics. Geological characteristics and parameters of soil layer are presented in Figure 6. The distance between ground surface and underground water level is 1.5 m. Based on geological records survey to identify the soil model parameters for the deep excavation stimulated in PLAXIS 3D. The shear strength parameters C and are determined from triaxial CU test. Soil modulus in Hardening-Soil model is defined as clay layers module EO_EDREF equals E50 REF equals .SU. SU is undrained shear strength of soft soil. The third layer, Silt sand from dense to loose. Module parameter E is chosen based on the correlation module E table of Bowles, 1988 or Malcolm Puller, 2003. The unloading reloading module is selected as UREF equals 3E50REF. The embankment soil layer has AREF equals 10,000 kN/m2. See analysis model. Analysis of the influence of the pile in the pit with the actual case. The subloading of construction machine and nearby building are taken 10 kN/m2 and away from outer edge of Larsen wall 2.6 m, located on natural ground surface. In addition, during the construction, soil is being moved and collected far from excavation about 1 m in the area of 200 square meters and 4 m in height, so the author decides 70 kN/m2. The distance between underground water level and natural ground surface is 1.5 m, Fig 7-9. A. 2D mesh. B. 3D mesh. A. Staged construction for the depth of 1.8 m. B. Staged construction for the depth of 3.8 m. Fig 9. Excavation profile for phase of staged construction for the depth of 1.8 m and 3.8 m, compared with the natural ground surface. D. Results and discussion. In actual field, the most leaning pile location is shown in Fig 10. In this section, the author analyzed the movement, cracking reason of the group of piles and compared with the slight deformation pit of experimental result table in field. From the calculate of PLAXIS 3D foundation under hardening soil, the author draws the biggest displacement of piles chart on excavation staged construction, Fig 11. At first excavation stage, depth of 1.8 m compared with ground surface, the small movement piles fluctuate gently and the largest displacement position is near the Larsen pile. However, at second stage, the large nearby soil mass, 70 kN/m2, causes a huge displacement on the group of piles near the wall. The displacement decreased gradually from head to bottom of pile. The largest movement are piles number 121, 122, 123 and 150, which have value in turn are 61.2 centimeters, 59 centimeters, 60.1 centimeters and 57.9 centimeters. The rest of piles range from 31.6 cm to 50.5 centimeters. During construction of excavation, the behavior of piles is also compared with the pile cracking resistance moment MCR equals 166.8 kN/m. When bending moment inside the pile exceed this value, pile is considered cracking. If the pile reaches 80% MCR, pile is assumed to reach the limited state. The largest bending moment inside the pile under the excavation construction is shown in Fig 12 and the result compared with Table 2. The bending moment of piles in PLAXIS 3D foundation stimulation gives 80% greater crack moment, it will lead to cracking. The results are also compared with the result of homogeneity of piles in field by pile integrity test. The group of piles numbered 150, 151, 153, 154 are great observable displacement because actually this piles group were cracked and pushed out. While stimulating by PLAXIS 3D, the piles material is linear elasticity, so they were not failure and keep the displacement status. Therefore, we not choose piles group of 150, 151, 153, 154 for analysis because of incorrect result. We choose piles group of 155, 156, 158, 159 instead. From the Table 3, we draw the chart of horizontal displacement of piles line, 155, 156, 158, 159, for each stage construction. When the first stage constructed, depth of 1,8 m compared with ground surface, we found that the horizontal movement of piles were quite small, fluctuated from 7.4 cm to 8.4 cm, and the more piles far away from Larsen wall, the more displacement value decreased. The piles above have the largest displacement at the height of 1.8 m compared with the ground surface, That is also the peak high of the pile. At this stage, we do not consider the observation in field. On the other hand, not the same as first stage, at second stage, constructed to 3.8 m, compared with the ground surface, we saw that piles have large horizontal displacement, and the largest movement of piles are all at the head of piles. The displacement value with observation value at the height of 3.8 m for each pile is, pile 155, 22.9 cm displacement, 26.5 cm observation, pile 156, 22.5 cm displacement, 19.4 cm observation, pile 158, 21.6 cm displacement, 13.7 cm observation, pile 159, 22.9 cm displacement, 18.5 cm observation. The largest displacement value of the piles line is analyzed compared with observation result are quite similar. As movement, pile moment near the wall have the greatest value, the more pile far from wall the more moment value of pile decrease, the pile moment away from wall with the distance of 4.547 m and 7.147 m, with the pile 150 and 153, have the alternately moment, 339.3 kN.m and 125 kN.m. With this result, the maximum bending moment exceeded the cracking resistance moment of pile, MCR equals 166 kN.m, appropriated with the homogeneous experimental result of piles in field. 3. Conclusion. When using the input number as table I to stimulate by PLAXIS 3D foundation on hardening soil produced the result of horizontal displacement and bending moment of pile approximated the observation value in field, so the input numbers are appropriate. The AREF of clay layers were chosen as equal from 200 to 400, with E50 REF equals SU. Thereby, we can analyze the reason piles group in buildings were failure and use this parameter for expanding the analysis to other situations. For the thick weak soil, clay loam, with the impact of large embankment load, 70 kN/m2, far from pit 10.5 m and the load due to construction machine and nearby construction, 10 kN/m2, away from the edge of excavation 2.6 m led to large bending moment displacement inside pile, exceeded bending resistance moment of pile and caused pile failure.